Hi, this video is on the ionic bond, and I'm following basically the order of chemistry, the central science. This is chapter 8, section 2 in that book, but again, any chemistry book is going to follow. It's going to cover ionic bonds at some point. Let's start. What is an ionic bond? Well, an ionic bond is basically a bond between two charged atoms. Charged atoms means they've either lost an electron or gained an electron, or it could be more than one electron. But basically you have two charged atoms that are attracted to each other because of the electrostatic forces between them. We call these charged atoms ions. And they're bonded to each other by that electrostatic attraction between the charges. So it's charge, it's a compound, as it were, that is attracted to each other because of electrostatic charges, okay, charge attraction. So you basically take this kind of bond really exists between the sides of the periodic table. And so you have on the far left side of the periodic table, say column 1, group 1, or group 2, column 2. These are metals of a sort, so you have alkali metals in group 1 and alkaline metals in group 2. These tend to take on a +1 charge in column 1 and a +2 charge in column 2. These are metals, and they are attracted to, say, the halogens in group 7, column 7, which tend to take on a -1 charge, or column 6 tends to take on a -2 charge. And so ionic bonds tend to form between the charged ion version of the elements that are on the sides of the periodic table between a metal and a non-metal, for example, sodium, which is in column 1, an alkali metal, and chlorine in column 7, which is a halogen. Okay? Ionic bonds, that is bonds based upon charge attraction, tend to form between elements on the edges of the periodic table. Now, the formation of an ionic compound tends to be highly exothermic. That is to say, when sodium chloride gets together into a compound, it's a very vigorous reaction that gives off lots of heat. You know, if you ever get a little sodium, you know, wrap it up in paper and throw it in a river and watch the explosion, or watch the bubbles at least. I'm sure you can find something like that on YouTube. I know there's a funny one about, I think it's either cesium or rubidium. It's not real, but it's pretending at how exothermic that would be. So when you tend to when a ionic compound comes together into a compound from two separate elements, it tends to give off lots of heat. The enthalpy change is very negative. What that means is that the compound itself is losing lots of energy, giving off lots of energy, lots of heat, and so it's exothermic. Okay. So let's talk about ionic bonds and electronegativity. So if you remember electronegativity, if you start at the bottom left of the periodic table, it has a very low electronegativity, and then as you go up and as you go over to the right, electronegativity seems to increase. Electronegativity, as you know, is the amount of energy it takes to dislodge an electron, as it were, to get rid of an electron. So it's very easy to lose an electron when we're on the far left side of the periodic table, and at the bottom, of course, the whole first column easily loses electrons. So there is a low electronegativity for all of the alkali metals in group 1, in column 1 of the periodic table. But as you go over here, like to fluorine, you're not going to get fluorine to get rid of an electron. We say that fluorine has a very high electron affinity. Fluorine's not in the business of selling electrons. Fluorine is in the business of buying electrons. Just like lithium or sodium over here, they're selling electrons. They're not buying electrons. So low electronegativity means that it doesn't take much energy to get them to get rid of their electron. So atoms on the far left of the periodic table. Now, how do they get to, so the octet rule, that atoms want to get to 8. They either want to get to it by giving them up, as in ionic bonds, or by sharing them in covalent bonds, which is the next video. So the atoms on the far left of the periodic table can most easily get to 8 valence electrons by giving one up. So sodium, lithium, they only have 1 valence electron in their outer shell. If they can get rid of that 1 electron, then their outer shell is basically the next next row down. So sodium, if sodium loses that one electron it has in its valence shell, and becomes sodium plus 1 by losing an electron, it loses one negative charge, so it becomes positive. So sodium's valence shell then is going to look like the noble gas on the period right above it, which is neon. And so, we've reached noble gas, so the octet rule is satisfied. Now, the loss of electrons is always endothermic. Now, I don't fully understand this myself, but I'm telling you what the book says, that when sodium loses an electron, it requires a gain of energy for sodium to do that. That is, the positive energy of the sodium has to increase for it to lose its electron. I don't fully understand this. The way I'm conceptualizing is that if you want to raise that electron to a higher energy state to get rid of it, that doesn't make sense either. Anyway, just trust me for now. I'll trust the textbook, and hopefully it'll be clear as we go forward. Loss of electrons by the alkali metals on the far left, always endothermic, requires a positive addition of energy to sodium in order for it to go to plus 1. Okay? So let's talk about electron affinity again. Electron affinity is the tendency to take or buy an electron. Fluorine, chlorine have very high electron affinities. They have very high electronegativity because you can't get rid of them. You can't get them to get rid of their electrons, which means that it has a very high electron affinity. Fluorine and chlorine want to get electrons. So atoms on the far right of the periodic table, like group 7, the halogen nonmetals, and group 6, they can get to 8 valence electrons most easily by adding electrons. So chlorine, which naturally has 7 electrons in its outer valence shell, all it has to do is gain an electron and it's reached 8. Noble gas. So chlorine has a high electron affinity and wants to take an electron and become a -1 chlorine -1. Then its valence shell will look like the valence shell of argon, the nearest noble gas. So opposite to the alkali metals, a gain of electrons is generally exothermic. That is to say that chlorine usually has to give away energy in order for it to gain an electron, and that's a negative enthalpy change because it's getting rid of energy. Again, it doesn't make common sense to me, but this is what the textbook says, and so I'm going to go with it. Okay, so just to visualize what we've been saying, and I took this chart from Wikipedia, it's public source. So these are the alkali metals and the alkaline metals. These, in their neutral state, only have 1 electron in their outer valence shell: hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. So for lithium, the easiest way for sodium to get to 8 electron in its outer valence is to get rid of that 1 electron it has. So when sodium gets rid of its 1 electron, it goes over here to neon, and it has basically a valence. It doesn't become neon because it still has 11 protons in its nucleus. But as far as its electrons are concerned, it has the electron configuration of neon, which fills the octet rule, and life is good. Similarly, chlorine has 7 electrons in its neutral state, but if chlorine can gain 1 electron, then it would have, again, a full 8 in its outer valence shell, and it would have the electron configuration of argon. It's still chlorine because it has 17 protons, but it wants all of these columns near the edges want to become like the nearest noble gas. So, and as far as electronegativity, as I was saying, it goes, from the bottom left to the top right. This column has a very low electronegativity, which means they give away electrons very easily. You don't even have to, twist their arm or anything. And these have a very high electron affinity over here, meaning that they want to take an electron very much. So that's kind of how that works. And so the metals over here and the nonmetals over here have a tendency to form ionic bonds. Once you get in here, once you get beyond +2 or 3, then we tend to shift to a tendency toward covalent bonds rather than ionic bonds. The reason is because of the lattice energy. So a lattice energy is the amount of energy required to separate a mole of a solid compound of something into its gaseous ions. So let's say I have a mole of salt, sodium chloride, and I want to separate, I want to blow that puppy apart until it becomes sodium plus 1 gas and chlorine minus 1 gas. How much energy will it take to do that? Well, you can look it up in a chart, of course. That's the lattice energy, the amount of energy to break, because the sodium chlorine tends to form a lattice kind of structure, like a cubic kind of structure, like a lattice. And so how do you figure out, let's say you don't have a chart, how would you figure it out? Well, basically you do it by way of the Born-Haber cycle. The Born-Haber cycle basically says that if you want to find the lattice energy to get sodium chloride from a solid to that ionic gas stage, you basically add up the enthalpy change, the energy change for each step along the way. Now there may be more than one way to get from A to B, but Hess's law says that no matter which path you take to get from state A to state B, the total amount is going to be the same. So it doesn't matter whether you go from state A to state B this way or from state A to state B this way. Hess's law says the total is going to end up the same either way. So the Born-Haber cycle basically says figure out the simplest way to calculate step 1, step 2, step 3, step 4, step 5. Figure out the simplest way to calculate how to get from one state to the other, add it up, and that's going to be the lattice energy no matter which way it actually does it in reality. Now, lattice energies are such that an ionic compound can really only go to like a +3. What I'm saying is that the amount of energy it would take to break a lattice apart is so great that this is why this is why we tend to go to covalent bonds once we get much beyond a +3 kind of ion. Okay, well, finally, how do we kind of talk about how much energy, if we're going to not calculate it, but kind of have a qualitative way to say this is going to take more energy than this? How would we figure that out? Well, this is called Coulombs Law. Coulombs Law says that the amount of energy, or the amount of attraction, that is, that two particles of some kind have, the amount of attraction is proportional to the amount of the charges, and it's inversely proportional to the distance. What this means is that the bigger the charge, the greater the attraction between the two, say, ions. And then the D means that the farther the distance, the less attraction there is. So as the charge goes up, the attraction between two charged particles goes up. As the distance goes up, the attraction between them goes down. And so we introduce then a constant, K, or kappa, however you want to look at it. And so now we can see that the lattice energy, that is the amount of energy it's going to take to break apart two ions that are in a compound, the lattice energy is going to go up as the charges go up. And then similarly, as the distance between the two the compound entities, as the distance goes up, it's going to be easier to break them apart. So the lattice energy goes down as the distance between the ions, as the distance goes up, the amount of energy to break them apart goes down, but the more charge they have, the more energy it's going to take to break them apart. That's just kind of common sense. So there you have it, ionic bonds.